Okay, welcome to the deep dive. You've sent over some really interesting source material for us.
Yeah, definitely.
And digging into it, there's this, well, unexpected connection. We're talking advanced math.
Right. Differentiation,
Oh.
integration,
Yeah,
that kind of stuff.
exactly. And how it somehow links up with designing food packaging.
It sounds a bit strange at first, doesn't it? Like two totally separate worlds.
It really does. But the sources you shared, they make a clear case. So today we're going to try and, untack that relationship for you.
Yeah, look at the scope, what it actually means.
And figure out what the material means by finding suitable formulations, the right math tools, basically, for problems like, say, calculating the volume of a food container.
Exactly. And, if you're maybe a college student wrestling with calculus right now,
Right.
this is a pretty cool way to see it jump off the page, out of the textbook and into something real you actually use.
Yeah, something concrete. So the core idea from the sources, it isn't just a vague hint that math might be useful.
No, no, it's much more targeted.
Right.
It focuses right on applying concepts from those specific calculus chapters on differentiation and integration.
And the sources connect this directly to integration in food science.
Precisely. And even more specific than that.
Okay.
The focus is really on the volume of food packaging design.
All right, so let's get into that. What does that link actually mean in practice? How is calculus integration specifically used to design a box or a bottle, or figure out how much it holds?
Well, think about what integration fundamentally is. It's a way to add up lots and lots of tiny pieces to get a total, like
Hmm.
area or in this case, volume.
Okay.
Now, figuring out the volume of a simple cube, easy basic geometry. But lots of packaging today is complex. Curved sides, weird shapes.
Like a fancy juice bottle or one of those squeeze pouches?
Exactly. Or even just the curve on a milk carton spout. You can't
Mhm.
just measure those easily with a ruler and get an accurate volume.
And that's where integration comes in, according to the sources.
That's what they highlight, yeah. It gives you the mathematical method to calculate the volume of those tricky shapes. You sort of slice the shape into infinitely thin pieces,
Uh-huh.
calculate the volume of each slice using calculus, and then integration sums them all up for the total volume. It makes complicated shapes manageable.
So that defines the scope then. It's calculus for complex packaging geometry where basic math doesn't cut it.
That seems to be the specific focus, yes.
Mm.
Within food science, it's this particular application for accurate volume calculation.
Got it. Now, what about that phrase, suitable formulation? The sources mention needing to find one. What's that about?
Ah, right. That's important. It basically means you can't just plug numbers into a generic formula. You need to um, translate the general idea of integration into a specific mathematical equation.
That actually describes the exact shape you're working with?
Precisely. So maybe a bottle's curve follows a particular function, y equals fx kind of thing. The suitable formulation is figuring out that function and setting up the correct integral, the specific calculus problem, using the bottle's dimensions to get the volume.
So the math has to be tailored. You don't just use one-size-fits-all calculus.
Well, the underlying principles of calculus are the same, but the application, the specific integral you write down and solve that, changes. Depends entirely on the geometry. A cylinder needs one formulation, a weirdly shaped ergonomic bottle needs a completely different one.
Okay, that makes sense. And the sources mainly talk integration for volume, but calculus also has differentiation. Does that fit in here too?
Yeah, it can, definitely. Volume's crucial. But designers also worry about other things, like using the least amount of plastic for a certain volume. That's optimization.
Ah, minimizing surface area for a given volume.
Right. Or analyzing stress points, or how easily something stacks, or even how quickly liquid pours out the flow rate. Differentiation helps find rates of change, maximums, minimums, all useful for optimizing the design based on constraints or costs.
So even within the specific volume focus, both integration and differentiation can play a part.
They often work together in real-world design problems, yeah.
Okay, so wrapping this up, the big takeaway from looking at these sources is, well, calculus isn't just abstract theory.
Not at all.
Integration, especially, is a practical tool. It has this defined role in figuring out the exact volume of complex food packaging.
And differentiation helps optimize things around that. It's about applying these powerful math ideas to solve real design challenges accurately and efficiently, making sure the package holds what it says it holds, using materials wisely.
Absolutely. So thinking about that idea of finding a specific, suitable formulation for each unique shape, here's something for you, the listener, to mull over. What other everyday objects do you think required someone to work out a very particular different or integration formula to actually create them? Lots to think about there.